Chapter 2, Measurement and Problem Solving. So here comes the math. The way it ends up is, well, we'll kind of be alternating between chapters that have math and chapters that don't have math. So that keeps everybody equally happy or unhappy, as it may be. I skipped section 2.1. I'm assuming there was a good reason that I did that. I can't remember what the reason was, but you should still read that in the textbook. We're going to talk about scientific notation, also sometimes called exponential notation. The thing about science is we deal with some really, really big numbers and some really, really tiny numbers. And we deal with that by expressing them in scientific notation. So in scientific notation, there are two parts. There's the decimal part, and then there's the times 10 to the something. This is the exponential part. So we have here a number that's 1 or greater and less than 10. So it's going to be a non-zero digit, and then it may be followed by a decimal point and some other numbers. But it's going to be 1 to 9, basically. And then that's times 10 to the something. This is the exponent. This is 10 raised to a power. So if the exponent is positive, that means that we've got 10 multiplied by itself n times. Or as this says, 1 multiplied by 10 n times. So 10 to the 0 means 10 times 10, 0 times. That doesn't make a lot of sense. I find it most convenient just to remember anything raised to the 0 power is 1. And if you're curious about why that is, go talk to the math department. I don't remember. 10 to the 1 is just 10. 10 squared is 10 times 10. And 10 cubed is 10 times 10 times 10. 1,000. Another way to think of this is the exponent tells us the number of zeros after the 1. So 10 to the 0 is a 1 with 0 zeros. 10 to the 1 is a 1 with 1 0. 10 to the 2 has 2 zeros. And 10 to the 3 has 3 zeros. So 10 to the 7 will have how many zeros? 7 zeros. Okay? So that part usually makes a fair amount of sense. When we do a negative exponent, things kind of get wonky. So the negative just means it's the inverse. So 10 to the negative 1 is 1 over 10 to the 1, which would be 1 over 10. And in decimal form, that's 0.1. 10 to the minus 2 is 1 over 10 to the 2. So that's going to end up being 0.01. 10 to the minus 3 is 1 over 10 to the 3. So it's 0.001. Any questions? No? So either everybody got it or everybody's so confused they can't formulate a question. We'll go with makes perfect sense. Clear. Clear as a bell, right? Clear as the air outside? Not today. So what we're doing with scientific notation is we're factoring out powers of 10. So we're moving the decimal place by multiplying or dividing by 10. So if we take this number, 5,983, that is 5.983 times 10 to the third. If you have your calculator, you can prove that to yourself. So 10 to the third is 1,000, right? So this would be 5.983 times 1 with 3 zeros. That's what 10 to the third is. So if you do that on your calculator, you're going to end up with that original number, 5,983. Let's think of this a different way. We're taking this big number and we want to bring it down to a more reasonable size. So if I take 5,983 and divide by 10, what do I get? I get 598 0.3, right? That would be times 10. So this is the same value as that. I'm just expressing it a different way. I don't know if any of you guys have children in public school these days, but you've probably heard about Common Core, and some people are all, ah. This is the sort of thing they're doing in elementary school now, which, if they do it well, is going to be awesome. But my kids, I have a kindergartner and a 4th grader and a 6th grader, and they're coming home and they're doing stuff like this, and I'm like cheering inside, because you guys were not taught this in high school or in elementary school. And I'm sorry that they didn't teach you this, but we're going to learn it now. What if we take this 598.3 and divide that by 10? I get 59.83, right? And there's the original 10, and then I pull this 10 out. Do you see what I'm doing? I'm pulling 10s out. I'm factoring 10s out. And so if I do that one more time, I'm going to get 5.983 times 10 times 10 times 10. This is 10 to the 3rd power. So that is equivalent to 5.983 times 10 to the 3rd. So we pull out however many 10s we need to get this number down so that it's between 1 and 10. I don't want to stop at 59.83 because that's too big. Another way to think of it is you've got one digit, a decimal point. You're never going to have 2 digits before the decimal point. This is standard scientific notation. Any questions yet? So that's the understanding where this comes from. Then there's the just rote do it method, which is probably more what you were exposed to in public school. So we look at this number, and there's not a decimal point there. But if there were, we would understand that it would be at the 3, after the 3. So what we want to do is we want to move that decimal point so that it's behind the first non-zero digit. So what these little loopy things here are is we're counting. So we're taking the decimal point from here and we're moving it over 1 place, 2 places, 3 places. The number of places I move the decimal point is this exponent. This number is smaller than 1. So I'm going to move the decimal point in the other direction. I'm going to move it 1, 2, 3, 4 places. This has an exponent of 4. I move the decimal point and I get 3.4 times 10. Now this one is negative and this one is positive. We're going to see a lot of things where we have 2 related concepts and we have to figure out how they match up. And so I like to come up with ways to help myself remember them, because I find memorizing, just flat out memorizing stuff with no understanding, to be very difficult. So this is how I approach this. I look at this number, 5,983, and I ask myself, is that a big number or a small number? That's a big number, right? Look at this one. Is this a big number or a small number? Small number. Okay, so big number. How do I feel about big paychecks? I feel positive about a big paycheck, right? Big number, positive exponent. This is small. I have negative feelings about small paychecks. Small number, negative exponent. That's not the way that it's presented in your textbook. Okay, so if the textbook method works for you, do it that way. But this is the way that it seems to work for most students. Any questions? So examples. Total U.S. national debt in 2010 was approximately, that's a really big number, right? Express this number in scientific notation. So what we need to do is we need to take the decimal point, that's actually a period, but the decimal point would be there, And we need to count how many places we have to move it so that it's after the 1. So this is grouped with commas. So I'm going to go like this. I'm going to go 3, 6, 9, 12, 13. I have to move the decimal point 13 places. That's factoring out 13 tens. So I'm going to write this as 1.2102 times 10 to the 13. And then I ask myself, big number, small number. That's a big number. Big number, positive exponent. So that one's done. Probably put a dollar sign in front. 1.2102 times 10 to the 13. This is not unlike expressing things in millions. You know, somebody's house is $2.5 million. Well, how much is a million? It's a 1 with 6 zeros after it. It's 10 to the 6th. So 2.5 million is the same as 2.5 times 10 to the 6th. It's the same idea. Express this number in scientific notation. Well, again, we're going to move the decimal point so that it's after the first non-zero digit. So we're going along here, zeros and zeros and zeros. We need to get the decimal point after the 3. So 1, 2, 3, 4, 5. So it's going to be 3.8 times 10 to the 5, but that's a small number, so it's a negative 5. That's not too bad, is it? We're going to put the decimal point behind the first non-zero digit. We're going to count how many places we had to move it. If it's a big number, the exponent is positive. If it's a small number, the exponent is negative.